Now in this section, we're going to bring together essentially everything you learned in this course. The idea is this. Given an arbitrary function, defined in terms of a rule, that's usually how we encounter functions, let's throw absolutely every skill we've developed at it in order to construct an accurate sketch of its graph. Now the word sketch is not to be misunderstood as some sort of hastily drawn rough scribble. Right? It's used to emphasize the understanding that our graphs won't be perfect. But whenever we sketch the graph of a function, we're making claims about its behavior, and these claims need to be accurate. So to start off, we're going to enumerate a list of key attributes of a function that we'll thoroughly investigate before even putting pen to paper as far as the sketch goes. So these first few lines just kind of reiterate what I've just said briefly. Right? We can apply the results of the previous sections, so everything we've learned up to this point, to produce graphs of functions. So each of these attributes are going to be carefully considered before you start. Okay, so the first thing you're going to want to think about is the domain of the function. Right? For what input values will the function work? Right? What values can you legally plug into the function in order to get a sensible output value? Because you're going to want to be aware of that. If the function is only defined for positive numbers, you're not going to want to be sketching anything on the negative half of the x-axis. Right? And vice versa. If a function is only defined on a certain interval, you want to make that the very first thing you're aware of in this process. For part B, the intercepts. So when does this function cross the x and y axis? Right? That's a key thing to consider. And by the way, the list here, the order is not that important. Although the domain should probably be considered as the very first thing. But aside from that, essentially these steps are done in increasing level of complexity. And in a sense, they kind of follow the timeline of our course as far as when we covered things. But really the only thing that matters is that you do the domain first. But everything else, you could follow this order just to create good habits. It's probably a good order to follow. But if you deviate a little bit here and there, it's not a big deal. But starting off with the domain, then the next thing be intercepts, right? Where does the function's graph cross the x or the y-axis? Find that right away. Remember how to do that? If you've got an equation involving y and x and you want to find the x-intercepts, just set y equal to 0 and solve for x. And that'll tell you where the x-intercepts are. If you want to find the y-intercepts, well, just set x equal to 0. And that will tell you the y-intercept. Okay, so that's part B. The next thing you probably want to think about are vertical and horizontal asymptotes. You don't want to skip that stage because knowing where the asymptotes are right early on is important. It's really helpful to make sure you don't make errors and go down a bad path that ends up, resulting in wasted time. So knowing where the asymptotes are right off the bat, the vertical and the horizontal ones, can save you some time in that you'll catch errors in your work a little bit more quickly. Once you've done that, then the stuff from chapter 4 kicks in. So for part D, we're going to look for intervals of increase and decrease. And by default, whenever you do that, you're immediately shown where the local extrema occur. So that's why these things kind of go together, intervals of increase and decrease along with local extrema. Really, why do you care about local extrema? You're not really trying to optimize the function, but you do care about when the function turns around, right? If it's increasing and then it turns around and starts decreasing and then it turns around and starts increasing, that's important information. And that's really exactly the information that you're looking for in step D when you go to sketch the graph of the function. Part E, intervals of concavity, right? What you'll see is partway along the way, what we'll typically do is we'll develop just a really general framework of the function that just has kind of when it's increasing and when it's decreasing. But that's not the whole story, right? Because if a function is increasing, is it increasing in a concave down manner? Like, is it arcing like this? Or is it arcing like this in a concave up manner? Right? So that's the information that you're going to get in part E. You're going to find out all the places where the function's concave up and all the places where your function's concave down. And then finally, in doing part E, part F will be pretty much immediate because E and F kind of go together. Once you've found the intervals of concavity, you also want to identify any of your inflection points. Okay, so these are all the things we're going to study. And then after we have all that information, the idea is you put it together and you sketch a graph of the function. So that's where we're headed here. So let's look at an example. We want to sketch the graph of this function f. So it's defined by f of x is equal to x to the 1/3 times 4 minus x. Or you could think this is the cube root of x, right? X to the 1/3 is really just the cube root of x. Let's go through the steps one at a time. So for the domain, that's part A, is your domain. What's the domain of this function? Look for any problems that might arise for certain input values. 4 plus x, that second factor, that's always defined. right? That'll never cause a problem. You can always plug any x value into 4 plus x. And what about the x to the 1/3? There's no concern there either, because x to the 1/3 is really the cubed root of x. And cube roots are defined everywhere, even for negative numbers. So there's no problem with the x to the 1/3 either. So if both of the factors make sense on their own, then so does the product, and therefore the function at any real number. So let's make a note of that. The domain of this function f is all real numbers. Okay, so that's our first one done. Okay, that was not too bad. Sometimes you have to do a little bit more work here, but in this case we didn't. For part B, we want to find intercepts. So let's start with the y-intercept. So the y-intercept, well, what are you going to do? Plug in x equals 0. So let's work out f of 0. That's going to give you 0 to the 1/3 times 4 plus 0. So this is just going to be 4. This 0 to the 1/3, 0 to the, that's a cube root of 0, which is 0. Right, so you've got 0 times 4, which is just going to give you 0. So the y-intercept is actually the point 0, 0. X-coordinate was 0, and the y-coordinate was 0. So the origin is the y-intercept. Let's get the x-intercepts now. And I said x-intercepts because there could be more than one in general. There might be none. There might be exactly one, or there might be plenty. Right? We don't know in general. So in general, there's, I should say, intercepts, because we should allow for the possibility that there's more than one. Okay, so to do that, you're going to look for points on the graph of this function whose y-coordinate is 0. So in other words, you want to solve the equation f of x is equal to 0. Or in other words, that's going to be x to the 1/3 times 4 plus x is equal to 0. Right, so those are the same thing, right? I've just written out f of x here instead of the literal notation f of x. This is the actual function. So when is this going to be equal to 0? Now, this will be true when either x to the 1/3 equals 0 or 4 plus x equals 0. Right, that's how you would solve an equation like this. It's already factored, so that's nice. So this is equal to 0 or this is equal to 0. So when does that happen? When is the cube root of x going to be 0? That's really what this is. The cube root of x is going to be 0 exactly when x is equal to 0. So this gives you the solution x equals 0, and this one's going to give you the solution x is equal to -4. Okay, so the x-intercepts now are going to be, well, they both have, any x-intercept is going to automatically have a y-coordinate of 0, because everything on the x-axis has a y-coordinate of 0. So this one has this x equals 0. That really corresponds to the point 0, 0. And then x equals -4. That corresponds to the point -4, 0. So really, here are the intercepts. I'll just put a box around them to make them stand out. Because really, and that's what you probably want to do, you want to summarize your conclusion at the end of every step, because it takes a lot of time. So by the time you finish going through every item in this list, it might be 20 minutes, right? So are you going to remember every detail that you worked through? Probably not. And if you can, well, that's great. But why make yourself do that? Why not write it out as clearly as you can so that you can just skim your work back at the end and focus on the sketching part and not have to remember any of the details of the work you did along the way? So going with that, even though the part A was very brief, why don't I just put a box around this as well? Because sometimes there might be work involved to find the domain. So once you've done that work, you want to isolate your conclusion of the domain so it's easy to see at the end. So now for our intercepts, we've got 2 intercepts. We've got 3 of them circled, but really there's a repeat here. The origin happens to be a y-intercept and an x-intercept because it's on both the x and y axis. So really we just got 2 intercepts to worry about. Okay, so get in a habit, and you should already be in a habit really, of summarizing your answer at the end of these steps, because in the previous sections, that's really what we focused on, right? We did all the work to solve these problems, and then we summarized our answer. So it's that habit is going to pay off here. Okay, so what about vertical and horizontal asymptotes? That's part C. So let's check vertical asymptotes. So I'm just going to write VA as an abbreviation for vertical asymptotes. And my claim is that there's no vertical asymptotes. And I haven't done any work to convince you of that. But I would just say it follows from the fact that the domain of f is all real numbers. Right? And this is certainly a continuous function. That's the other piece of it. You can have a function whose domain is all real numbers. It still has vertical asymptotes, but not if they're continuous. Right? This function f is continuous. It's built from continuous operations. X to the 1/3, that's a radical. 4 plus x, that's a linear function, so it's continuous. It's a product of two continuous functions, so f is continuous function. It's continuous everywhere on its domain, which is all real numbers, so everywhere. So if its domain is all real numbers and it's continuous everywhere, you're not going to have any vertical asymptotes. So there are, let's say that there are no, or I'll just say there are none, because f is continuous on all of the real line. Okay, and then what about horizontal asymptotes? Okay, I'm just going to use HA for horizontal asymptotes. Remember how we find horizontal asymptotes? You want to take the limit as x, limit of the function as x gets very far away from the origin in either direction. So you're going to want to compute, well, for starters, you want to take the limit as x goes to infinity of f of x. So what's that going to be? That's the limit as x goes to infinity of x to the 1/3 times 4 plus x. So what's happening? Let's just analyze each of the factors first. As x gets very, very large, what's happening to 4 plus x? If x is going to infinity, what difference is adding 4 going to make? Because that's what really this is. It's taking x and adding 4 to it. If x is already going to infinity and you add 4, the result is still going to be going to infinity. Right? So let's observe that first. This is going to infinity. And then what about x to the 1/3? The cube root of x. If x is going off to infinity, the cube root of x is also going off to infinity, just a little bit slower, but it's still going to grow arbitrarily large. If x is getting arbitrarily large in magnitude and is positive, blowing up in the positive direction, so is x to the 1/3. So we can make the observation that this is also going to infinity. So you got the product of two factors, both of which are getting arbitrarily large in magnitude. Well, that means the product is also going to become arbitrarily large in magnitude. So this limit is either going to be positive infinity or negative infinity. And since each of the two factors are both positive in the sense, right, they're both going to positive infinity, you've got no negative factors appearing. You're just going to, the result is going to be positive as well. So this limit is going to end up being positive infinity. Okay, so that, well, that's the limit in one direction. What about the limit in the other direction? If we want to check for horizontal asymptotes carefully, we are going to want to check in the other direction as well. The limit as x goes to negative infinity. So let's do that. We want the limit as x goes to negative infinity of x to the 1/3 times 4 plus x. So let's just kind of ask the same kind of questions. If x is going to negative infinity, what's happening to 4 plus x? Well, if we plug in 10 million here, and then, or negative 10 million, that's a really large negative number, and you add 4, you're really going to get negative 9,999,996. That adding 4 really doesn't change it that much. Right? And so if x is exploding in the negative direction, adding 4 is not going to change that. Just like it didn't change the fact that x was exploding in the positive direction in the previous limit calculation. Right? So adding or subtracting a constant is not going to change the fact that something's going to either positive or negative infinity. So this is going to negative infinity. And then x to the 1/3, again, remember that's the cube root of x. Draw a sketch of the cube root function. Right? There's room for it over here. If you're ever confused about this, I'll do it over here actually. The cube root function just looks something like this. Right? It's not perfect, but that's what the cube root looks like roughly. And so that's the function y equals x to the 1/3. As x gets very large in the positive direction, this blows up in the positive direction as well. It grows arbitrarily large. It just has this kind of downward arc. It's concave down, but it's still growing arbitrarily large. And then same with as X, on the other direction, if X blows up in the negative direction, this comes down arbitrarily large in the negative direction as well. The Y coordinate, it just follows suit. It just isn't. It's always, the Y coordinate will never be as large as the X coordinate in magnitude, but it will for any point on for any point on the negative half of the y-axis that you draw, eventually, and if you were to cut now a horizontal line across corresponding to some point on the y-axis, this curve would eventually burst through it. It's not going to be bounded at all. That's the idea. So the point is, this goes to negative infinity as well. So you've got the product of two factors that are both growing arbitrarily large in magnitude. So the product is going to grow arbitrarily large in magnitude as well. So the result is either going to be positive infinity or negative infinity at this stage. But since both of the factors are negative in the sense that they're going to negative infinity, you can just think of it as two negatives canceling out to give you a positive when you multiply them. So the result is actually going to be infinity for this as well. Okay, so we've got no vertical asymptotes, and we've actually got no horizontal asymptotes either, because the limit in either direction was positive infinity. But this information is still important. Okay, so we're going to come back to this when we draw our sketch. The fact that you know that very far to the right, the function explodes up, and very far to the left, the function explodes downward. Right? That's important information when you draw your sketch, knowing what happens on either end. Remember what that phrase is, determining the end behavior of the function? That's really what it's kind of built into part C here. When you're looking for vertical asymptotes, and then you look for horizontal asymptotes afterwards, you're really determining the end behavior of the function. And even if you don't find any horizontal asymptotes, the information that you get is still going to be important. So that in this case, let's just summarize our conclusion. The only important information here was that the limit as x goes to infinity of f of x is equal to infinity, and the limit as x goes to negative infinity of f of x is equal to infinity. Right? So I'll put therefore in the sense that this follows from the work we just did. Do you need to actually write this? We did just do the calculation, but remember, you're trying to minimize the amount of material that you need to read through at the end of this process when you go to sketch your graph. Because if I look at the time now, we're 17 minutes into this process, and yeah, it's taking a bit longer because I'm explaining it as I go. You'll be a little bit faster once you get into the habit and you just do these steps automatically without having to explain what you're doing. But by the time we're done, by the time we get to the end of part F, we might have taken, it might be another 15 minutes before we're finished, and that's a long time to forget the details. At the end, you just want to be able to quickly scan your work and just see, okay, that's important information there, there, and there, right? It makes it a lot easier to read. So we'll do part D on the next page.